Hello everyone. My name is Kush Vora and I am going to present on PUF for hardware security in IoT devices using machine learning model and adversarial attacks. So this is going to be outline for my presentation, starting with the introduction, followed by why physically unclonable functions in IoT systems are necessary, and then the different threat models based on that, few of the adversarial attacks and their types, the FGSM attack in detail, the mitigation strategies to overcome those FGSM attacks, and ended with a summary. So let's move forward. And the introduction. The document provides detailed information on various vulnerabilities in system on chip and Internet of Things devices, including categories, weaknesses, attack patterns, and consequences. In SOC, vulnerabilities encompasses issues like privilege separation, incorrect privilege assignment, inadequate permission handling, and unauthorized access. IoT threat models concentrate on adversarial attacks targeting machine learning models, privacy risk associated with physically unclonable function based data, and data poisoning attacks on PUF based systems. Understanding and addressing these vulnerabilities and threat models are crucial for ensuring the security of SOC and IoT devices. The next is why PUFs are necessary in IoT systems. Firstly, for the device authentication. In simple terms, in an IoT system, PUF are used to add extra security. Think of PUF like fingerprints for devices. Each device has its own unique fingerprint that's based on its physical properties, like tiny differences in how it was made or its environment. This fingerprints helps ensure that only trusted device can connect to the network or access data. It's like giving each device its own special key that can't be easily copied or stolen. So POPs make IoT systems safer by giving each device its own unique identity and making it harder for attackers to break it or impersonate devices. The next is security. In PUF-based IoT systems, security works a bit like a secret handshake. Each IoT device has its own special secret sort of fingerprint. This secret is based on tiny differences in how device was made or how it works. So in simple terms, PUF-based security for IoT is like giving each device its own special secret code, making sure only the real devices can join the network and keep everything safe from imposters. The next is key generation. Imagine each IoT device has its own secret treasure chest, but instead a key it's locked with a special puzzle that only that device can solve. This puzzle is based on unique features of devices like tiny differences in its hardware. So in simple terms, key generation in PUF-based IoT means each device creates its own secret key using its special puzzle, ensuring that only trusted device can understand and communicate securely with each other. The next is anti-counterfeiting. Think of PUF-based security like a special stamp that only genuine products have. Each IoT device gets its own unique stamp based on its individual characteristics. When you buy a product, you can check its stamp to make sure it's real. Similarly, in PUF-based IoT device have their own unique stamps that prove they are authentic. This makes it really hard for someone to make fake device because they can't replicate the unique stamp. And last but not the least is low overhead. In simple terms, low overhead in puff-based IoT means keeping things running smoothly without using up too much energy or resources. Imagine each IoT device is like a car. Low overhead means making sure that car runs efficiently using just the right amount of fuel to get where it needs to go without wasting any time and money. The next is threat models. The first one, adversarial attacks. So adversarial attacks on machine learning models, it's when someone tries to fool smart computers into making mistakes by subtly changing the input data. The next are privacy risks for puff based data. It's risk that someone could sneak a peek at private information stored in super secure system that's based on unique device characteristics. And the last is data poisoning. So it's when someone tampers with the data that secure systems rely on, tricking them into making mistakes or behaving unexpectedly. Now the adversarial attacks. So, adversarial attacks refers to a class of technique where subtle, carefully crafted permutations are added into input data with the goal of forcing machine learning model to make incorrect predictions or classifications. These perturbations are often impeccable to human observations but can lead to significant changes in the model's output. So basically, adversarial attacks are like that the attackers could minutely change the to get the correct output from it. So basically, this getting like a changing the input and getting anything in output. Now, the examples of adversarial attacks, starting with misclassification of image. Imagine you are teaching a smart camera to recognize animals, but then someone sneaks in a picture of a banana and tells the camera it's a giraffe. That's like misclassifying image, fooling the smart program into seeing things wrong, fraudulent transactions. Think of online shopping, but instead of buying real stuff, someone tricks the system into thinking they are buying things they shouldn't. It's like pretending to buy a fancy car with monopoly money. This is what happens in a fraudulent transaction. The last is malicious email. Imagine you are checking out email and you see a message that looks like it's from your friend, but it's actually from a sneaky stranger. They trick you into clicking on a link that installs bad stuff on your computer. That's like malicious emails. They look harmless, but they are actually trying hard to from computer to steal your data. The autonomous vehicles pictures a self-driving car cruising down the road. Now imagine someone hacking into its system and making it think a stop sign is actually a speed limit sign. That's like a sneaky attack on autonomous vehicles. Impacts of adversarial attacks. The first one is degradation in model performance. It's like teaching your smart friend to recognize animals, but someone keeps messing with the pictures, so your friend starts getting all the answers wrong. Adversarial attacks can make smart computer programs like those in machine learning. The next is potential security risks and consequences. Imagine you have a secret code to unlock your diary, but someone figures it out and reads all the secrets. Adversarial attacks can expose sensitive information or cause damage, like hacking into secure systems, stealing data, or disrupting services. Loss of trust in machine learning systems. Think of relying on a friend who's usually good at giving advice, but then they start giving you wrong directions. The next is different types of adversarial attacks. The first one is FGSM. FGSM basically stands for fast gradient sign method. It's like a trick a bully uses to mess with your smart friend's answers by making it tiny changes to the questions. The next is black box. Imagine trying to solve a puzzle, but you are blindfolded and can't see the pieces. In the world of computer programs, a black box is like a puzzle you can't see inside. It's a system where you don't know how it works or what's going on inside, making it harder to figure out the manipulate. Next one is white box. Now imagine solving the same puzzle, but this time you can see all the pieces and how they fit together. That's like white box in computer terms. The next one is data poisoning. Thinking of baking a cake, but someone sneaks in a bad ingredients when you are not looking. Data poisoning is like that someone messes with the information used to train smart computers, like adding wrong answers to the test, which can make them give incorrect results or behave unexpectedly. The next one is an evasion attack. Pitchers playing tag, but instead of running away from someone, you are trying to dodge a security system. An invasion attack is like that. Someone tries to trick a security system or smart program by sneaking past its defenses or fooling it to thinking they are allowed, in which they are not. Optimized based attack. It's like someone figuring out the best way to hit a target with a slingshot by testing different angles and speeds. The last one is an optimist based attack. It is when someone carefully tweaks their strategy to find the most effective way to fool or break into a system. Now we shall discuss FGSM in detail. FGSM or fast gradient sign method is like a clever magic trick for fooling computers that recognize image. Imagine you have a picture of a panda and you want the computer to recognize it as a panda. FGSM works by figuring out tiny changes you can make to the picture that won't noticeable to human eye but will completely confuse the computer. It's like tweaking the pixels of panda picture just a little bit so that when the computer sees it, it thinks it's something else entirely, like a gibbon or a guacamole. It's like a simple yet powerful way to show how vulnerable some computer systems can be to small calculated manipulations. The next is mitigation strategy for FGSM. So before discussing the mitigation strategy, we shall see about the FGSM attack with its practical implementation. So this is an FGSM code. Firstly, for FGSM, we use torch and matplotlib.plyplot to form the graph in an Python code. Firstly, we pre-train the model with ResNet model, and then we pre-process it using transforms code. Now we have defined the FGSM function attack. So first, what we do is in the perturbed image, we add image with some of the perturbations so that the a machine learning model could understand that what's the problem with the image, and feeding more and more of this data could help machine to learn more about what type of perturbations the actors could or the attackers can cause to it. So this codes will basically gradient the input and change it into a similar sort of object but with different colors and combinations. So here, for example, I have taken cat image of an cat. So as we can see that the image of the cat is gradiated, its colors are changed, it has some bright sort of effects on it, so machine could not able to recognize it as an cat image. So now discussing the mitigation strategy. So first we need to load the data set, pre-process it, and define the convolution neural networks. We compile the model with optimizer, loss functions, and metrics. So this optimizer, loss function, and metrics basically are used to measure the accuracy of the device, accuracy of the code, so that at what percent the machine is able to understand the code. So we have defined the function for generating adversarial examples and for adversarial trainings. Here, the entire dataset is divided into two parts. The first half of the dataset is considered as a training dataset, and the rest is used for as a testing material for our code. So adversarial training is performed by generating adversarial examples from training data and updating the model parameters based on these examples. Finally, we evaluate the model on test data to ensure its accuracy. So this is how we can mitigate the strategy. So for example, if we take an assembled database, here TensorFlow libraries of Pythons are used um, to show the accuracy and to measure to train the machines for the input. First, we load the MNIST dataset. So what's MNIST? MNIST is basically a dataset that's the code of the handwritten things. So here the handwritten letters are given as an input in form of a dataset towards the machine. So here's layers are used to add the sequential measures into our machine. Then we have created an ensemble of models. Then we use optimizers, loss, and matrices to measure the accuracy of our code. Then the process of training is done by creating a function to generate adversarial examples and to evaluate them. So output of this code is like this. Different epochs are run to measure the accuracies. So by running the initial epochs, we can measure the accuracy. Then the accuracy keeps increasing with each epoch run. So at the end, the accuracy is 0.98. That's equivalent to 98%. So that this code is efficient to 98% of the time, gathering about the permutations of the attackers. These are the following data sets that can be used to evaluate the machine and train the machine for the data. So basically, MNIST. MNIST is an image, a big collection of pictures, but instead of cats and dogs, it's all handwritten numbers from 0 to 9. MNST is like a special set of these features that people use to teach computers how to recognize different numbers. It's a popular dataset used to train and test machine learning models, especially for recognizing handwriting. Cipher 10 picture a bunch of small images like photos of everyday objects such as cars, trucks, birds, and airplanes. Cipher 10 is the dataset that contains these types of images, but each picture falls into one of 10 different categories. People use Cipher 10 to test and train machine learning models, particularly for tasks like image classification. And last is Cipher 100. Similarly to Cipher 10, but even more diverse. Instead of just 10 categories, Cipher 100 has 100 different categories ranging from animals to vehicles or household items. It's used for more challenging tasks in machine learning, where the model needs to recognize a broader range of objects and categories. So the code of Cipher 10 is not much different than the assembled data. Just in place of MNIST dataset, we have loaded Cipher 10. Then the same procedure of creating model, generating adversarial examples, training with the adversarial examples, and at the end a main function is called. And the accuracy of the MNI of the Cipher 10 will always be less than the MNIST because it has broader and wider range of outputs and inputs. So accuracy would be around 88%, but the code can give an accuracy about 71%. And the accuracy for the Cipher 100 would even be less than the Cipher 10 because it has very broad range of inputs and images to be classified. So the summary. Physically unclonable functions provide a robust foundation for security in IoT devices, leveraging the inherent variations in hardware components to generate unique identifiers. When coupled with machine learning techniques, PUF-based security in IoT device becomes even more patent. By training machine learning models on the responses generated by PUFs, devices can authenticate themselves, detect tampering, and ensuring secure communications without relying solely on traditional cryptographic methods. This approach offers several advantages, including resistance to cloning attacks and low overhead in terms of hardware resources and energy consumption. Additionally, machine learning algorithms can adapt to evolving attack strategies, enhancing the overall resilience of IoT systems against security threats. However, challenges such as variability in perf responses and potential adversarial attacks on machine learning models need to be carefully addressed to realize the full potential of this integrated security approach. Thank you.